All right, so I am hitting record. I don't have a specific order. I guess I'll just start. If anybody has any specific questions that they want to ask, can you just say, I have a question in chat? And that way we can kind of get just an order going.
I had one about I was going back and like starting on the first unit and kind of working my way up, but there was the star diagram thing with the vectors, if you know what I'm talking about. I literally cannot remember how to do that.
Yeah, vector
I
star.
think I just need a refresher.
Sure. So when you're looking at vector star, they're showing you something like this, where you've got sort of it's all centered on there. So this is the vector star. But if you were to take this vector right here and move it over to here. So I moved it over here, and I took this vector and moved it up here. What you would get is this triangle shape on here. So what you're doing, they're kind of asking you, hey, if you have these three vectors,
If I get that, I'm just
move them around on there, what would you be able to, like which triangle would you be able to make on there? So there's only one, in the direction of these arrows, there's really only one triangle you can make with these. One tip for kind of figuring out if there's a couple answers that are close, where multiple ones would make sense, you can look at, say, this vector, for example. Let's say this one starts at -4 and goes up to 5 on here. By the way, this is mirrored on my end. Does this look normal?
Yeah, let's
Okay, all right. So so this vector would be the vector -4, 5 on there. So you would have to kind of look at all your different examples and see if there's a vector that goes -4 in this direction and 5 up.
okay.
Answer the question, you think?
Yeah, I just definitely needed that refresher, but that's good. Thank you.
Yep. Okay. Yeah, again, if somebody else wants to ask a question, I guess I don't know what people were hoping to get out of this, but I don't have, I'm not going to be able to cover a whole lot. So if you have specific questions, I'll just keep going with those. Maybe let's try this. What are some topics that people are worried about? Like what are some, or maybe think of a question that you got wrong on the exam. You can go back and look. Refresh on how to do integrals. Sure. So there's two topics with integrals. One of them is being able to do an antiderivative, and the other one is being able to use that fundamental theorem of calculus. Sorry, I'm just adding people as they come in. So we can maybe talk about these examples here. Shut the door real quick. So these are the two types of integrals. This is a definite integral. This is an indefinite integral. You know this one's a definite integral because it's got the 1 and the 5 up there. But if you want to take the antiderivative of this one, if you're trying to figure out the antiderivative of this, we have a rule that says for x to any power, you just take that power and add 1 to it. So I'm going to add 1 to this. And then secondly, you take whatever that number is and divide the whole thing by that number. So this integral is going to be 1/4 x to the 4th from 1 to 5. Right? Just letting people in as we go. So can you, if people are asking questions in the chat, can you ask it to everyone, just so other people can see it? Thank you. Now, for this definite integral, we need to think about this being integrated from 1 to 5. So one thing I'm going to do is I'm going to take this 1/4 out in front. So we can use constant to take that out in front, and what we're left with is x to the 4th evaluated from 1 to 5. This evaluation from 1 to 5 means that if you think back to the fundamental theorem of calculus, right, what we're doing with the fundamental theorem of calculus is we're saying if we take the integral of little f, then that's going to be equal to the integral of, or sorry, the antiderivative at f minus the antiderivative of 1. This thing that I've got here, 1/4 x to the 4th, this is my capital F. So I'm saying capital F at 5 minus capital F at 1. So the answer for this one would be 1/4 times 5 to the 4th minus 1 to the 4th. Five to the 4th, I'm not sure what that is off the top of my head. Throw that in there. $625. Right? That's for definite integrals. If you have numbers here and here, you'll just need to plug them in to the antiderivative. For something like this, for a definite integral, you'll just need to take the antiderivative of it. So a big tip for a lot of these is you may want to rewrite something like this. I'm just going to close something here. So you may want to rewrite something like this in order to use that rule that we just used over here. So rather than calling this x to the 1 over x to the 4th, I'm going to call this x to the negative 4th. Just like here, where the rule was, add 1 to the exponent and then divide by that number, we're going to do the exact same thing here, right? So x to any power, as long as it's not -1, we can use that rule. So this one here, this is going to be again, adding 1 to this is going to be to the -3. And I take that result, second, and divide by that. So this is going to be divided by -3 times the -3rd. In this case, we don't have to evaluate it at any numbers on here. So we're not saying from 1 to 5, since there's no numbers here, indefinite integral. We can just say plus C here. One thing I would do with this is clean up this notation a little bit. So I would, like we took it 1 over x to the 4th and change it to x to the -4th. I would put it back into a form that's a little easier to read. So this is -1/3. And then that x to the -3 is this x to the 3rd down the bottom there. Still that plus C there. That's the basics of doing integrals. Most of the time, you just need to use one of those easy 5 rules that I wrote down for antiderivatives. But you do want to think about rewriting them, right? Like a lot of times you'll have to rewrite them. Another example where you might have to rewrite something would be if you have this integral of 3x squared divided by plus x to the 4th divided by x to the 7th. Right, this is a situation where you want to split this up into fraction. That way you can just evaluate this integral and then evaluate this integral. Other than doing the substitution rule, that's the basics of integrals. So I'm just going to check the chat. Okay. Finding the length of a vector in a unit vector in a unit cube, normal vectors, angle between planes and distance between planes. Okay. The question concerning parallelogram and 2 sides of the vector given. Intersect lines intersecting polygons. Limits, distance between planes. Distance between planes. Find the tail of the vector. Okay. So I'll start basic and I'll work my way up to finding the distance between planes on here. If you look back at the lecture notes, I think for some of these problems where you're finding the distance between 2 planes, I think the best thing you can do for that is look back to the lecture notes and look at the example that I have written down there, since there's there's worked out examples of everything I'm about to show you, but just starting with those basics. If you have a question that says, say move vector move the vector tail, or so that the tail is at 1, 2, 3. And let's say something like find the head of the move vector. I'll tell you where A and B are. So let's say point A is equal to 0, 1, 0, and B is going to be equal to 5, 5, 0, or 5, 5, 1. So for this one here, you want to think about, I think a lot of you know how to find this vector AB, but you want to think how you're making that vector. So I'm going to draw this line here. Let's see, you've got the vector AB. So a lot of you know you take the tip minus tail on here, right? So 5 minus 0. The second one's going to be 5 minus 1. And this will be 1 minus 0. That's 5, 4, 1. If you think about what you're doing with this, in each of these instances, you're looking at the x, y, and z components of B and A. So this is Bx minus AX. This thing here is By minus AY, BZ minus AC. When you take that vector, let's say, so AB looks like this. When you take that vector AB and you move it to this new spot over here, so that its tail is at this point 1, 2, 3. We're moving that vector over here, and this is what we're trying to find. So here's 1, 2, 3. Here's what we're trying to find. I'm going to call this point, usually they give you a name for this one. I'm going to call this C, and I'm going to call this D, right? Now, when you're looking at this vector here, the first part of this problem says, hey, I gave you 2 points. Tell me what the vector is between them. Right? A much more common problem that you'll see, or a good second part for this, is I'm going to tell you the vector and one of the points. You tell me what the other point is. So we're going to take kind of this process here, and we're going to convert it over to this example here. So if all we're doing is moving the vector, that vector 5, 4, 1 is going to be exactly the same. So you might even be able to think about this as being 5 plus 1, 4 plus 2, 1 plus 3. But if we think about it formally in our equation here, so we're trying to find D, we're trying to find the head of that vector. We're going to look at
She's
somebody's mic is on, you might not realize it. So we don't know all of these values on here. What we do know is that the vector that we're interested in is 5, 4, 1. We don't know what Bx is. We know that Cx, though, is going to be 1. C1 minus Cy. Cy is 2. Dz, we're not sure of, but Cz is going to be 3. Now you've just got 3 equations. You're trying to solve for dx, dy, and dz. First equation is set that 5 has to be equal to dx minus 1. 4 has to be equal to dy minus 2. 1's got to be equal to dz minus 3. So as it turns out, the point D is going to be equal to looks like 6, 6, 4. And you can see that if you draw this diagram here, you can see that that adds up the same way. So that question comes up a lot on exam 1, just being able to take a vector and move it around. But this is the this idea here that you can kind of split up a vector into the tip minus the tail, individual points. You should be able to solve if I give you 2 pieces of information, like 2 points, you can find a vector. Or if I give you a vector and a point, you should be able to find the other point on there. So I wanted to make sure that we got that one because that's a skill that you have. Another skill from this is taking a vector that's got a magnitude. So this is something somebody asked about is if I give you a magnitude and I give you a direction, can you tell me what that vector might look like? So let's say, make sure I'm looking at. Okay, so suppose a vector
Alo ạ. Alo.
somebody's mic is on. It's answering a call.
Alo.
Magnitude of 3 and a direction so usually the way this is mentioned is it's that it's parallel to something like 1, 5, 10. So what we want to do here, and I'll just say this 3-dimensional vector here has a magnitude of much more than 3. Right? If you think about the magnitude of this one, it's going to have 100, 25, and 1 as its components, and you'll square root them. But we're going to have to take whatever that vector is, and the idea is we're going to have to shrink it down so that it has a magnitude of just 3. Okay, so in order to figure out how that vector would look, we're just going to figure out how long this vector is, the original 1, 1, 5, 10. We're going to shrink it down to 1. That's called a unit vector. And then we're going to multiply it by 3. So that's kind of the process that we'll use here. We're going to take this vector, shrink it down to a unit vector that has a magnitude of 1, and then multiply it by whatever magnitude we need. Okay. So figuring out the magnitude of this one here. If we want the magnitude of 1, 5, 10, that is going to be equal to, so we use this notation here. Or use these like double lines here to talk about the magnitude of that vector. But the formula for this is sort of like a Pythagorean theorem or like a distance formula on here. where we square, take the square root of all the squares of this. So let's see, 100, 25, 26. So I'm just going to leave it under the square root like that, but this is some number. So I'll repeat it again. What we're trying to do in this three-step process is we want to take this vector, this is the original vector, we want to shrink it down to 1, and then we're going to multiply it by whatever magnitude we want down here. So this vector here (1, 5, 10). The first thing I'm going to do with that vector 1, 5, 10 is I'm going to divide it by square root of 126. I'm dividing it by this value here so that I can shrink it down to 1. And then I'm going to multiply by 3. So anyway, this will be, I'll write down what this might look like. So this would be, this is times a scalar, right? So this is sort of like, right, 1 divided by square root of 126 times this, and this. Also multiplied by 3. So this would be 3 divided by 126. This would be 15 divided by square root 126. This would be 30. If you look this up, like I'd really like you to think about it as being like this, sort of shrink it down to this and then expand it out here. If you're looking and trying to compare that to what you see as like a formula in your book, this piece here, this is your unit vector. Right, the formula for a vector divided by its magnitude is just a unit vector. And then multiplying it by 3 gives you that vector that you're looking for. One second, let me just see. Okay. Okay. Questions concerning a parallelogram when 2 sides are given. Vectors, and it asks for the endpoint of diagonal between the vectors. Sure. So this is a and by the way, I've got the volume on. If anybody wants to pipe in and ask a question about anything that I'm doing, I'm happy to answer those. So if these are 2 vectors, and let's say that these make up a parallelogram, if these two vectors make up a parallelogram, what they're saying there is that, so I'll call them U and W. So that first vector U looks like this, and W, well, I should have drawn this down here. U looks like this. U looks like this, and W looks like this. Right, something like that. Sorry, I'm going to change this up so I can draw this more easily. So if this is U and this is W, then if you just have two vectors, you can kind of create a parallelogram based on that by just copying those two vectors on there. So here's kind of another W and here's another U on there. So if this point here, and they will provide this point to you, you know, if this point is 1, 1, 1, and they're talking about the diagonal of that parallelogram, the diagonal of the parallelogram starts here and goes here. So if you want to figure out where that point is, I'll draw it again over here. You've got 1, 1, 1. You've got a vector U and you've got a vector W. You just need to add those two vectors together. So this point here is going to be 1, 1, 1 plus U plus W. Oh, sorry. I forgot we were working in 2 dimensions here. So this is just going to be 1, 1. So anyway, this point here would be 1 plus 2 plus 3. And this point here would be 1 plus 1 plus 10. So starting at this point, U takes you here, W takes you here. That's what the diagonal is. It's just the addition of those two vectors. Again, if you're just joining, yes, I am recording this. If you're just joining, you can put questions in the chat and I'll kind of answer them as we go. I think for the distance between planes and the angle between planes, I can do a quick angle between the planes problem on here, but I'm going to share the where you can find this in the notes. Yeah, so I'm looking at section 1.5, this last one here. That goes over 2 types of questions where we talk about the angle between planes. And then You've also got this equation for the distance from a plane to the origin and the distance between two parallel planes on there. So I'll start with a little discussion about plane equations on there in the normal vector, and then hopefully that'll be enough to kind of help you through these examples here. So somebody's asking if there's going to be a practice final in there. No, the final exam is just cumulative. So if you look at practice exams 1 through 4, and then quiz 10, that'll cover all the content that'll be on the final. So I can't get more specific about what exactly is going to be on the final. Like I can't say like don't study this and study this, but there'll be some questions from quiz 10. There'll be some questions from every section on there. Okay. So I'll start talking about planes a little bit. So one plane equation there's a couple forms that we have for plane equations. One of them, let me straighten this out. One plane equation we have is that if you have a normal vector, it's A, B, C, and you have a point on the plane. So this is a point, not a vector. If you've got a normal vector A, B, C, you've got a point on that plane, X naught, Y naught, Z naught. So there's no point on the plane. That's my normal vector. Then the two forms that this plane equation can have, one of them is A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught is equal to 0. That's one form of the equation. So if I give you a normal vector, A, B, C, and I give you a point, X, Y, Z naught, you can fill in everything but the X, Y, and Z in here. That'll give you the equation of the point. Another way to write all of this out is to say, let's just multiply everything out. So this form just keeps A times X plus B times Y plus C times Z. And then it takes all the extra stuff. So those are all numbers that you would know, right? Like 3 times negative or 3 times 7. You would throw all that out and puts it over on this side of the equation and calls that value lowercase d. So a big skill that you're going to need is to be able to take an equation like this and figure out what its normal vector is. So we'll talk about that in the context of a problem. So let's say we've got two planes. Plane A, we'll call plane 1. As the equation N1 has that equation, plane 2 has this equation, let's say. Something like that. Thinking about, and so we're trying to find the, say, find the angle. Your formula says that you should first find the normal vectors of these two planes and then figure out the angle between those normal vectors. Because the argument goes something like this. You've got a plane like this and a plane like this, and you're trying to find the angle between them. You could just look at normal vectors of those two planes. A little nicer. If you draw the normal vectors of those two planes, that this angle here is the same as this angle between the planes. Right. So we're going to find two normal vectors, and then we'll figure out the angle between them. So my first normal vector, I can just look at the numbers out in front of X, Y, and Z and say that my normal vector for plane 1 is going to be 3, -2, 7. My normal vector for the second one is going to be these numbers out in front. So if you look at this form, it's going to be some number times X minus the point, B times Y minus the point, C times Z minus the point. So this normal vector is going to be 4 for the X value. This, there's nothing out in front here, so that implies a +1. This out here is going to imply a -1. So once you get these two normal vectors, then you can plug it into this formula here. You can say that here for a second. So N1 dotted with N2. So this is the dot product, this is the magnitude of N1, this is the magnitude of N2, and that's multiplied by cosine of the angle between them. So the form that you end up with to find this final answer, I'll put it over here, is that cosine, or I'll give it kind of the final form. You would figure this out, and this out. And then you would say cosine of theta is equal to N1 dotted with N2 divided by magnitude of N1 times magnitude of N2. And the last step would be to take the inverse cosine of both of these. Right, so that would give you your angle between them. One skill that you'll definitely have to use, and I mentioned it before, was you'll have to be able to figure out what if I give you a point and a normal vector, you should be able to create both of these equations here. By the way, this lowercase d here is just, I'll write it out. Ax naught plus b y naught plus c z naught. But you'll see that, you'll figure that out if you just put it in this form and then write everything out. One thing that they can do instead of giving you a normal vector and a point on this plane is they might say something like this. They might say a vector goes through the point 1, 2, 3, and it's parallel to plane 1 on there. So rather than telling you what the normal vector is, which would tell you what A, B, and C are in this equation, they're saying it goes through this point and it's parallel to this plane. What that means is this is your x naught, y naught, z naught, and then you're going to steal the normal vector from this plane over here. So if two planes are parallel to each other, they're going to have normal vectors that are parallel to each other as well. So a plane that goes through the point 1, 2, 3 and is parallel to this plane would have a normal vector 3, -2, 7. And you would use that for your ABC. This is your X, Y, Z. I'm going to check on the chat, see. Let's see. Okay, so somebody's asking about projecting lines intersecting polygons. I'll go over that one more time and then I'll talk about limits. So I think I'll share my screen for that. Okay. Is this what you were, I'll assume this is what you're talking about with the lines and planes, unless you tell me otherwise. But the process is always going to be the same for this one. So it's a 5-step process. First thing you're going to do is just draw a point. So draw your intersection, draw your point, label it P. Transfer the point. So you're going to transfer that by taking it down here. One thing you'll have to think of when you're transferring that point down to the other plane is whether it's going to intersect here or here. We talked about how you know where it's going to be intersecting because you can look at, so I know that this point P is going to intersect down here at the bottom because I'm looking at the line that P is on up here. So the line P is between these 2 points. And these 2 points, if I transfer those down, correspond to this point and this point here. So you'll have to think about which line it's on when you transfer it. But that's step 2. Step 3 is to draw the line segment. So this is different from what is happening here, right? So this is the line kind of poking through, this dashed line here is the line poking through the polygon. This down here, this line segment that you're going to draw represents the plane. So we're kind of comparing the plane and the line. Those are the 2 things that we're trying to compare with each other. The line is this black line here. The plane is this line segment that we've drawn here. So what we've figured out, or what we can figure out in step 4, is we can figure out which is in front, the line or the plane. Now, if we're only looking at the line segment, so I'm going to kind of block out everything that's not this line segment area, right? If I block everything else out and I just look at that narrow hallway there, when we figure out what's in front, our arrows come from the bottom here. Excuse me. And so we see that the first thing it hits from the front is the plane, and then it hits the line. So our conclusion from this is that the plane is in front of the line. If we know the plane's in front of the line, right? So you kind of picture, here's your plane, here's the line behind it, right? So that means the line is going to be hidden on that part. So what we can see up top here is that between P and I, the line is hidden. If we saw that the line was in front down here, right? If the black line was in front of the orange line that we just drew, then we would draw a solid line there. That takes care of whether it's dashed or solid up here. Then we kind of repeat the process here. Then we would repeat the process, taking a point from down here and transferring it up there. I'm trying to find a worked out. Here we go. So this is a good kind of breakdown of everything that I'm doing on there. But if you want just the 5-step process, that's what we're looking for. Is that there? Okay. So for limits, I kind of I'm drawing a blank about what exactly we discussed about limits. I almost feel like that was last semester that we worried about that. Is there a specific limit question that you wanted to ask? If you put that up, then I can answer it. But I feel like we didn't. Oh, you might be talking about like that limit definition of like this. If you're talking about this, we can work with that. But here I'll find find a relevant question on here. So something like this. I can show you some of the basic things that you'll want to do for this type of problem, but really this is just a lot of algebra, kind of like working everything out so that you're not dividing by 0 anymore. So I'll kind of, I'll talk a little bit about this. Generally, and then give you some hints for it. So this limit problem here, if you just try to plug in h equals 0 into this, you would get 2 minus 2 divided by 0 plus 1, so 0 on top. And then you would get also 0 on bottom, right? So 0 over 0 is, it's not even undefined, it's even worse than that. It's something called indeterminate, where like it could be infinity, it could be negative infinity, it could be 1, it could be 0, we don't know. So what we need to do is rearrange this somehow so that we're not just dividing by 0. Right? So all of this work that I'm doing here, the whole point of that is to just get that h so that I'm not dividing, just getting that h and kind of figuring out how to divide it on there. So each step in here, this is just all algebra. So I'm like taking that 1 over h out. I'm multiplying both of these by h. I'm taking out that common factor of 2 over h. I'm combining these two fractions, so I'm making a common denominator between them. I end up with h on top, h on bottom, so I'm canceling it out. But like all of that work is just to get that h out of the denominator by itself. So all of these are going to require some amount of algebra to get them to that point. But once you do, you'll have some kind of simplified version of this. So that would be your 2 divided by h plus 1. That'll be this one here. So you would choose number 2. And then thankfully, the second step after you've simplified it in that way, once you've simplified it, now you're allowed to plug in h equals 0 on there. So once you plug in h equals 0, then you would get 2 divided by 0 plus 1, which is just 2 divided by 1 or just 2. So yeah, that's this type of problem is really just a matter of doing the algebra to simplify it so that you're not getting that h in the denominator. For that limit definition of a derivative, I didn't see a whole lot of problems that used that particular setup on there. I think this is the only one I can think of that used limits, but I might be wrong, and you can correct me on that. Okay. Let's see. So finding the length of a vector, I'm just going over some of the other questions that I'm seeing. Finding the length of a vector is just finding its magnitude. So that was that square root that I put up earlier, square root of all the different elements of that vector squared. Normal vectors, here's a problem that you can use, I think this came up a couple times, is how to use the cross product to find the normal vector. And I'll take it from like really bare bones here. So let's say there's 3 points on the plane. So let's say they're 1, 1, 1, 0, 1, 1, and 0, 0, 1. So these are 3 points on the plane here. And they asked, what is the equation of the plane? So you know that to figure out the equation of a plane, so I'll kind of I'll draw our final goal here. If we can figure out the A, B, and C, and we can figure out X naught, Y naught, and Z naught on here, then if we can fill all those in, then we'll have the equation of a plane, this plane specifically. So for a plane, we need a point on the plane, and we need a normal vector. So I'm drawing this kind of sloppy, so I'm going to have to erase it to work this example out. But for a point, our X naught, Y naught, Z naught, we can use any of these 3 points. We have already figured that out. But for the normal vector, we're not told that. We're going to have to figure that out. So the way to figure out the normal vector using these is to think about what this plane might look like if we drew it out. So here's our plane with 3 points on it, A, B, and C. One trick that we can use is we can say that, let's just call it these 2 vectors here. So like CB and CA, those are both vectors on the plane, right? So because those 2 vectors exist on the plane, we can use that to figure out our normal vector. The normal vector is something, and I'll see if this shows up on Zoom okay, but the normal vector sort of sticks out of the plane, right? So we've got 2 vectors on the plane, CA and CB, and then this normal vector sticking out. Because of this relationship, where both of these are right angles on here, we can use the fact that the normal vector is going to be equal to the cross product of the vectors that we just created. So CA and CB. Since we can find the cross product of these two vectors and find the normal vector, the reason why is the cross product makes a perpendicular vector. It's perpendicular to both of them. So I am going to figure out what these vectors are. And by the way, I could have chosen different vectors here. I'm just kind of choosing an intentionally weird set of examples here to show you, but just to show you that any two non-parallel vectors will work for this. So CA, again, we're just going to do tip minus tail. So that's going to be 0 minus 1, 0 minus 1, and 1 minus 1. And tip minus tail, so that's going to be this vector is -1, -1, 0. And then CB, tip minus tail again, so 0 minus 0, 0 minus 1, and 1 minus 1. So that vector is going to be 0, -1, 0. The normal vector will be the cross product of those two. So you can either throw these into GeoGebra, say cross of these two. We'll just do it really quickly here. Normally the order of these cross product vectors matters, but the only difference that you'll notice, if you switch the order of these is that you'll get, instead of getting this normal vector, you'll get the opposite normal vector, but that would matter in the equation for a plane. Either way. So that vector you remember the process here, we're going to get bring up the x, we get -1 times 0 minus this is going to be 0. The y, we get this times 0, this times 0. So that's not going to give us anything interesting here. Covering up the z, we get -1 times -1, which is +1 minus 0. So it turns out that normal vector is going to be 0, 0, 1. This is your A, B, and C. So this whole stretch of the equation is just going to be 0, since A and B are equal to 0. C is going to be 1. Z minus, pick any of these on here, right? The Z naught for all of them is going to be 1. Or Z equals 1 is your plane there. You may have a more complicated answer depending on, if these points are kind of given a little more interesting values on here, but yeah, that's your That's how you take 3 points and turn them into the equation of the plane. Thinking about an example that's also using knowledge about planes. I'm going to erase some of this. Well, maybe that's, I'll see if anybody has any more specific questions before I keep talking about planes more. Oh, sorry, I wanted to talk about the, because that's sort of related to that, is finding the vector in a unit cube on there. But let's see, finding distance of a segment when you have a vanishing point. Okay. For that, but I want to talk about that unit cube. Somebody's got their mic still. I think it might be you, Noah. Thank you. Okay. So actually, I'm going to answer not a unit cube question, but a kind of a larger rectangle problem. So kind of finding those diagonals. So let's say they give you this rectangle here. Hopefully that's showing up at least a little bit on here. And let's say they tell you that this is one point they're interested in, and this is the other point they're interested in. Show up a little clearer. So they say, take these 2 points on the unit cube here and find the vector, or maybe find the magnitude of that vector there. Your task with this one, let's say that they tell you that this is 2, this is 5, and this is 6. The dimensions of that rectangle are just going to be width of 2, length of 5, height of 6. So you can look, if you're trying to find this particular vector here, you want to think about what the coordinates of those 2 points are. All right, so from there you can figure out the magnitude and whatever else you need to about something. But if you look at this point here, this is our x-axis, this is our y-axis, this is our z-axis. If you look at this point here, moving in the x direction, there's no movement in the x direction at all. So the x-coordinate of this is 0. Think about the y-coordinate of this, no movement at all. It's just hanging out right on the z-axis. And the z-coordinate of it is 6. This one down here, if we think about the x-coordinate of it, that's sort of like how far it's moving in or out of the page. It's moving 2 up here. So 2 in the x direction, and then we move, you can almost trace a path here, right? 2 in the x direction, 5 in the y direction, And then the fact that it's on the bottom of this rectangle tells you that Z is 0, right? We didn't have to move, not up to this one. This would be 2, 5, 6. But this is 2, 5, 0. If you want to figure out this vector here, you might just call this A and B and say that vector AB will be equal to 2 minus 0, 5 minus 0, and 0 minus 6, right? Tip minus tail. So that's your vector there. Same thing with the unit cube on there. Nice thing about the unit cube is right, all the dimensions are just 1, 1, 1 on there, but it's the very, very same problem. Somebody was asking about the distance of a segment when you have a vanishing point on there. Okay, so Mackenzie, was that about the, you're thinking of like maybe that brick problem where you had like 3 bricks and then I added a 4th brick onto it? Is that, okay, sure. So I think I have a video of that. I think if you watch the video that I posted on that YouTube channel, that has me going over an example of that. Let me just look it up. I'll link it in the chat. It's the same spot. I'll put this okay, so that's the link to the video on there. If you look at the, I'll figure out where exactly it is here, right at the right around the 15-minute mark. Maybe 45 minutes is when I start doing this problem, but I'll lay out the process really quickly. But yeah, I think that'll be easier than trying to draw that out on the chalkboard. You know, feel free to like and subscribe while you're visiting it. And then exam 3 word problems. Okay. Right. So I'll break down that distance one, and then we'll talk about one of the word problems on there when we do optimization. So let's say you've got some, really testing my drawing skills here. Let's say that you've got some bricks that have this vanishing point here. And let's say that in reality, I'll actually make it, I won't have them be the same length. So if that version that I did in the video, all of them are the same length, but let's give them some different lengths here. So let's make it really extreme and say this one's 1, this one's 5, this one's question mark. Right, let's say we were not sure what that one is. Yeah. Okay. So in reality, right? In reality, the length of these are 1, 5, and let's say 7. And we need to figure out how long these should be, right? Like what these measurements up top here should be. And let's say this one is let's call this 1.5. So the process for that is to look at this perspective over here and draw a second one over here. So this is your actual vanishing point in the drawing. We're going to call this V2 and set that up to be your second vanishing point. Draw a parallel line underneath here. Actually, I'm going to draw this a little closer. Then I'm going to take these points here, 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 and here. And I'm going to connect them with my vanishing point and this line that I've drawn down here. So just sort of highlighting, so this is, all right, I'll draw it down here. This is, right, your 1/2, and this is, I guess you'll have to be given this. Let's say this is 3. And then this is your x that you're trying to figure out, like the distance, or this length of a unit in here. So create another vanishing point that's kind of horizontal to that one. Draw another horizontal line, connect all these vanishing points, and then I'll try and highlight the things that I'm going to redraw here. So this line, this line, this line, this line, and this line. I'm going to take those and redraw them, and also all this stuff here. I'm going to take that and redraw it. This is 1/2. This is 3. This is x. And then from there, you can put your original, like, actual measurements of these things. So not in the drawing, but like in reality, you have 1, 5, and 7. Now you're just doing one of those. Now you're just doing one of those cross ratio problems on there. So you could label these, right? A, B, C, and D. A prime, B prime, C prime, and D prime. And from here, you are taking the cross ratio. All cows bring dairy. All dogs bite cats. So figure out all those lengths on there, figure out this cross ratio, use that to figure out that same cross ratio, which is over here. That's the case if you have them different lengths on here. If they all have the same length, the process is exactly the same, except you can just put, you know, even if they don't tell you what that length is, I think they do in the problems that we looked at, but if you just call that, you know, just give it a name, Z, 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 right? If they're all the same, this cross ratio will just end up being 4/3. So that was sort of a shortcut that we could use. But in this particular example, you need to, you'll have to put in 1, 5, and 7. That's what we'll go get here. There. Garden edging, asking for total cost given an area. Sure. So I actually worked out, I think I'll just go over one that's in the notes that I worked out because I think I have an example of all of these worked out on here. So if you look at the, share it. If you look at the notes under exam 3, I've got the ones that I did in class. So I did this garden one, I did the profit and like design team on there, and I did this beam one. And then if you look at this more word problem sections, I have everything kind of laid out for all of these, but I can talk more generally about them. So maybe I'll look at, I'll start by looking at this. Well, let me look at the window one. So, so what's common about all of these in terms of what I'm going to be asking is I'm always going to be asking, what are we trying to minimize or maximize? I'm going to try and put that into an equation, right? So here I'm trying to maximize the light. And I can say that the light from, it's the total light's equal to the light from this top part plus the light from the bottom part. It's going to be 1/3 as much light in this top part. So I put a 1/3 out in front. And then area of an equilateral triangle or area of a, you know, semicircle. Those are things that I had suggested you memorize that equilateral triangle one. And then once you've kind of like got an equation for the thing that you're trying to maximize or minimize, now it's time to take all the other information that you have and try to fix your equation that way. So here, the extra information that I got was that the outside perimeter of the window is 28 feet. So that means that this measurement, right, all the way around, that window, all the way around that window has to be 28. So x plus y plus another x on here. So 3x plus 2y has to be equal to 28. I'm taking that and putting it into my light equation. So just to go over, I'll go over some other problems, but I'll kind of show you that we're doing the same thing every time. We're always just figuring out what are we trying to maximize, simplify it, all right, try and write an equation for that, and then use a constraint or use the other information in the problem to try and get rid of one of these variables. And then from there, I think probably the easiest part of it is knowing that once you have that equation, if you want to find the maximum, just figure out where the derivative is 0 in there. Or figure out, or plug the equation in, see if you can find where the top and the bottom of it are. So looking at this problem here, we're trying to minimize the total heat loss in there. So there's no drawing for this one, right? But they're describing a solid rectangular tank with a square base, so we can draw that. And it says, again, what are we trying to minimize or maximize? We're trying to minimize the heat loss. So I'm going to write an equation for the heat loss. We get a certain amount of heat loss from the sides and a certain amount of heat loss from the roof of this tank. They're telling us that these sides lose heat at 14 calories per meter squared. This loses heat at 2 calories per meter squared. So there's like, that's sort of like the dark and light window, right? They're letting them out different amounts of light. I wrote an equation for the heat loss here. I had to name some variables just like I had to do here. I had to say, these are all X's, these are Y's. This is another X down here. So I just gave names to these variables that I was looking for. Once I had an equation for the thing I'm trying to minimize, then I took the other information in the problem. That's the fact that this volume is 1924. Coming up with an equation for the volume, I can get rid of one of these variables. So in this case, I found an equation for H and I got rid of that H. Same thing. Take a derivative, set it equal to 0, figure out where the minimum is. For this one here, I'm trying to maximize area, so I came up with an equation for my area. This one was really easy to figure out this equation. There's no simplifying that needed to happen. The difficult part was all the extra information on there. So all the extra information was kind of how much this fencing costs. And each side of that fencing costs a different amount. So I drew a diagram for this one that says the cost is going to be, so this particular side costs, so the 10 and 30 were just examples I was throwing out to, explain this problem to somebody. But if this is the north side costs $3 per foot. So the cost is going to be 3 times whatever this measurement is, 3 times W. So that's why I come up with this 3W, $4 per foot on the east side, which is this one over here. So that's going to cost $4 times L. Take that equation, figure out a way to eliminate one of your variables, derivative, set it equal to 0, find the maximum on there. That's going to be the consistent objective for all of these. This profit one on here, we're trying to maximize profit. The weird one, or the weird thing about this one was that there's a difference between this capital P value and the profit on there. This was the amount of profit per plan, so we needed to multiply it by Q. But once we did that, we take the other information, use that to get rid of one of the variables. In this case, we got rid of capital P. Set the derivative equal to 0, find the maximum. So each time you're kind of going through that process, and if you look at the examples I posted, I did an example of every single type of problem that you can see on there. So if you, want to kind of like study it that way and think about what am I trying to maximize or minimize in each of these cases, that would be one way to study this. You can kind of just think about what am I trying to maximize or minimize, and then see what that looks like in each of these different types of problems. I'm just going to check the chat again. Question with the octahedron from exam 1. Okay, let me just find that. Really quick, so I'm looking up an octahedron. I'm having trouble finding a, let me, 1.5. Okay. Okay, I'll go ahead and share this one. Okay. So this is a non-rectangular octahedron, but it's connecting the center of all these faces on here. So the first thing to do with this one would be to recognize what these 3 points that make this up on here. So we can kind of ignore everything that's not this. We can ignore everything that's not this green triangle here, but we're forming an octahedron based on these 3 points on here. And when they say that at the center of each of those faces, on there, we know, for example, that this one, that this face right here goes out to 2, and looks like this is going out to 7 and goes up to 12 on there. So if we want 2, 7, and 12, so if we want the center of that face there, that's just going to be half of each of those values on there. So this point is going to be 1, and then the y coordinate is going to be half of 7, or 3.5. And then half of 12 would be 6. Once we do that with all 3 of these points here, so this one would be, well, sorry, let me think about this a little bit here. actually, this is not, I forgot about the fact that, so those are the half values of everything on there, but this one actually goes all the way, this point goes all the way out to half of the X value, all of the Y value, and then half of the Z value on there. So this would actually be 1, the full 7, and then half would be 6. This one here would be, also kind of fill it out one at a time. On here, this point here would be, it looks like it goes all the way up to 12. So I'll put the full 12 there. Halfway. So that would be 1 and 3.5. This one here would be oh, sorry, the X goes to 3. Is that what somebody's? Oh yeah, thank you. Yeah. So this would be, sorry, these would be 1.5. I forgot it goes, yeah, out to 1, 2, 3. Thank you. So that's 1.5, and that's 1.5. And then this point here goes all the way out to 3, halfway. So we get 3, 3.5. And 6. Okay. So earlier, I showed you how you can take 3 points and figure out a plane equation from that. So you can take these 3 points to make a plane. And then once you've got that plane set up, I'll go ahead and let's see. Once you've got those, oh, that's between parallel planes. Okay, so now you've got that. Once you've got that equation for your plane, you should have your A, B, and C, and you should also, and you can use any of the 3 points on there, X naught, Y naught, and Z naught. That'll give you lowercase d on there. Then you can use this formula here, where you divide it by the magnitude of your normal vector. So square root of a squared plus b squared plus c squared would give you this. And then the absolute value of that would be your distance from the plane to the origin. So yeah, kind of very involved example, but you know, just take it one step at a time. First step is figuring out those points on there. I think for questions about you know, concepts, I think now that you have a sort of base understanding of a lot of this stuff, now is the time where you can go and look back at the textbook. That'll have, worked out examples of kinds of different things and all the formulas that are kind of, organized a little better in the sections that you're looking for. I think learning from the textbook originally is maybe a little bit difficult because everything's kind of thrown at you all at once. But if you know what you're looking for, in a particular section, then that should be relatively easy to find what you're looking for in terms of a formula. Let's see, I'm trying to look back in the chat and see if I answered everything. Oh, there was something where a vector's been multiplied and then translated on there. So I'll go over that. And I think that'll be the last thing I can go over today. So I suppose a vector is parallel to 2, 3, 1, and has a magnitude (10). If tail is at 1, 1, 1, where is the head of the vector? So for this one, really the only thing that's changed, the only thing that's changed about this is this phrase, a vector is parallel to this one. So we want to think about that vector being parallel. If two vectors are parallel to each other, let's say this is a vector, and this is a vector. The vector v and 5 times the vector v are parallel because they're pointed in the same direction. They're just sort of have different magnitudes on here. Another example of this might be something like -5 times v. That's also parallel. It's going in the exact opposite direction. So when we talk about what it means for something to be parallel, we're really just saying that if this vector times some number is equal to this vector times some scalar is equal to this vector, then they're parallel. So what that looks like in the equation is we could say that a vector is equal to some number k times b vector. If this is true, then a is parallel to b. All right, if we can multiply it by some number on there. So talking about this vector being parallel to some other vector, we can say, let's say the vector we're trying to find is, right, that's the one we're trying to find. So we could say, first of all, that V is equal to K times this vector here, 2, 3, 1. Another way to write this would be, we could say, we multiply this K by all of these on here. So we could say this is, right, 2K, 3K, 1K on there. Figuring out the magnitude of this vector here, the magnitude of that vector is going to be the square root of 2K quantity squared plus 3K quantity squared plus K quantity squared. So that's going to be equal to, again, just the same idea that we did with the other problem, where we want to shrink it down to 1, the unit vector, and then multiply it by 10. So let's see, magnitude of V is going to be equal to 4K squared plus 9K squared plus K squared. So 14, overall 14K squared. Or put another way, square root of 14 times K. All right, so I just took the K squared out. K there. Okay, so we have an equation for the magnitude of this thing. And if it's parallel to that and has a magnitude of 10, our vector here is going to be this vector here. So K. Two, 3, 1 divided by square root of 14. Okay. Times 10. So we're going to get rid of this K on the bottom, K on the top. From here, we're figuring out this vector. We're just going to multiply these all by 10 and divide everything by square root of 14. So the first one will be 20 divided by square root of 14. This next one will be 30 divided by square root of 14. And then 10 divided by square root of 14. That tells us the vector. If the tail is right here, that means it's starting at 1, 1, 1 and going this far. So the head or the end point of the vector V is just going to be 1 plus this. So the head of that's just gonna be 1 plus 20 divided by square root of 14. 1 plus 30 square root of 14. 1 plus 10 square root of 14. And this is a point here. Coordinates. I think the big takeaway that you want to take from this is when you see that two things are parallel to each other, I want you to immediately think that, like if it says A is parallel to B, I want you to be thinking this equation here, right? That A equals K, some number K times B. That's what tells you when two things are parallel, that's usually going to be the missing piece of finding the answer here. So, all right, that is all I've got time for. I do have to leave at 6, so I'm going to put this up. Hopefully tonight I'll be able to put this up, but I'm going to process this. I'll put it up on YouTube, and I can make an announcement as well that it's up there. But thanks for the semester, everyone. Let me know if you have any last minute questions. All right, you're very welcome. Good luck with your studying. And yeah, I will have a great summer. It's one of the perks of teaching is the summer. So.
Hi, I have a question real quick.
Yes.
Are you allowed to tell us how many questions will there be on the exam?
25.
25. And
Mhm.
I wasn't sure if I missed it or not, but I did ask about, do we have a practice finals?
Yeah, so I answered that. The only questions that there's no practice final, but look at practice exam 1, 2, 3, and 4, and then also quiz 10. That'll everything on there.
Okay, so do those 4 practice and quiz 10, and I should be good, right?
Yes.
All right, thank you so much. Have a nice one. Have a nice
You're
summer as well.
welcome. Yep, good luck with the final.